The headline says, Tennessee data centers must pay for their own power lines, but this isn't just a tax bill or a new regulation to debate in city halls. It reveals a stark engineering reality. The physical limits of our electrical grid have become the true bottleneck for artificial intelligence growth, not the speed of the chips themselves. For years, we assumed data centers were passive consumers that would simply plug into existing infrastructure and grow as needed. That assumption is now breaking down under the weight of hyperscale demand. Today, we trace how a new law in Tennessee exposes the deeper constraint. The multi-year timeline required to build transmission lines clashes violently with the rapid deployment speed of AI clusters. We will look at why these facilities are no longer just customers but active drivers of grid expansion, and what this means for the future of compute when the lights can't keep up with the demand. The traditional model of electrical engineering relied on load diversity to maintain stability. In a standard city or region, power consumption is spread across millions of individual devices. Lights turning off in homes, factories shifting shifts, electric vehicles charging overnight. These small fluctuations smooth each other out, creating a relatively predictable aggregate curve that utility engineers can manage with existing buffers and reserves. However, the rise of hyperscale AI campuses has shattered this assumption. A single modern data center drawing hundreds of megawatts acts less like a collection of individual loads and more like a massive city-sized load appearing all at once. These facilities do not just consume power, they swing it in synchronized bursts with millisecond-level precision as training jobs ramp up or inference requests spike. This synchronization creates transient instability that standard utility buffers cannot absorb. When an AI cluster ramps up, the grid experiences a sudden demand shock similar to flipping thousands of air conditioners on simultaneously across a state, but concentrated into one facility and repeated continuously over days rather than hours. The result is not just high consumption, it is frequency volatility that threatens cascading failures. We saw this play out in July 2024 in Northern Virginia, where the synchronized load swings from data centers contributed to a fault that tripped 1.5 gigawatts of capacity off the grid. This incident was not caused by a software bug or a chip failure. It was a physical limit hit hard when the rate of change exceeded the mechanical inertia of the transmission system's generators and transformers. Quick resource note, I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The scale of this challenge is quantified in recent modeling that treats regional grids like ERCOT as proxies for future demand scenarios. The data projects that by 2030, AI data centers will account for roughly 17.5% of total electricity demand in key regions. To meet this need without collapse requires an 83.6% increase in generation capacity over the next decade. This is not a marginal adjustment, it is a fundamental shift from implicit coexistence to explicit co-design. Hyperscalers are no longer waiting for utilities to build out lines and then moving into sites that already have power available. They must now design their own generation and storage assets alongside their compute racks because the physical timeline for building new transmission infrastructure simply does not match the speed of AI deployment. The mismatch in timelines is where the engineering crisis lives. A major hyperscaler can deploy a cluster of advanced processors, ship them globally, and have them running at full capacity within 1 to 2 years. In contrast, constructing the heavy industrial assets required for high-voltage transmission lines, permitting, land acquisition, steel delivery, civil construction, takes 5 to 10 years. This creates a dangerous window where compute hardware is ready long before the grid can support it. The new Tennessee law forcing facilities to pay for their own infrastructure is essentially an acknowledgement that waiting for utility-scale expansion will stall progress indefinitely. It forces data centers to become microgrids in themselves, managing their own frequency regulation and load shedding because relying on public stability has become too risky. This shift toward off-grid AI represents a fundamental architectural pivot. Engineers are now treating power generation and storage as primary system constraints rather than utility services provided at the plug. When you build your own battery farm or solar array to backstop a data center, you are effectively decoupling from the grid's volatility for critical operations. This is not just about keeping servers running, it is about preventing the kind of synchronized load swings that destabilize regional grids. The financial mechanisms behind this, whether companies pay directly for transmission upgrades or build their own generation, are still being defined in academic frameworks and market innovation, but the engineering necessity is already here. The narrative that data centers are simply paying for their own grids requires nuance because it implies a simple transactional relationship. In reality, these facilities must co-design with utilities to ensure synchronized stability. They cannot just drop hundreds of megawatts into a node without coordinating how that load interacts with the rest of the system's inertia. The optimal mix favors rapid solar and storage deployment alongside thermal flexibility, but the physical bottleneck remains the speed at which we can move electrons from generation sources through transmission lines to the cooling racks inside these buildings. We are entering an era where every new AI breakthrough faces a hard limit, not in code or algorithms, but in copper wire and concrete transformers. The constraint is no longer just about how fast a chip can calculate. It is about whether the physical world can deliver enough stable power to keep those calculations happening without triggering a blackout. As we move forward, the story of artificial intelligence will increasingly be written by electrical engineers building transmission lines rather than software developers writing models. The emerging reality that AI data centers are becoming the primary drivers of grid expansion forces us to rethink where the limits lie. The true bottleneck is not the silicon in our servers, but the thousands of miles of wire needed to power them, a physical constraint that dictates how fast we can scale this technology forward. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.